Okay, so let's have a look at parity as a means of error detection. First up, if we start with simple one-dimensional parity, this is really just adding a bit onto the end of every byte, or using a bit in every byte, in order to add a simple check. And in this case, is the number of ones odd or even? And you can have odd parity, where you set that last bit to make it so that there are an odd number of ones, or you can set even parity, where you then will have a 1 if it's required to make that byte have an even number of ones. So this is a really, really simple kind of approach. Two-dimensional parity does this within the bytes in that way, but also actually adds a check over a set of bytes. And it might be all the bytes in the frame, or it might be a group depending on the particular algorithm and implementation. And the advantage of this is that over one-dimensional parity can't tell if two bits have been switched around. So if one bit that was a 1 becomes a 0, and the bit next to it that was a 0 becomes a 1, one-dimensional parity can't tell that that's happened. With a two-dimensional parity, if it's moved in one dimension, you can tell because it won't have moved in the other dimension, and so you can pick out the error that way. And so as a result, two-dimensional parity can essentially catch all 1, 2, and 3-bit errors, but not all 4-bit errors. It can catch many of them, but not all of them. So we'll look at a practical example here. We have the 2 dimensions of parity. So this means that if we go across, we want there to be an even number of ones in each byte. So there's 1, 2, 3. So it's an odd number. We need one more 1 to make it even. So we add 1 into the parity bit. In the next byte, we have 4 of them. That's already even. We don't need an extra 1, so we put a 0. This byte, we have 5. That's odd. We need it to be even. So we need to add an extra 1. Likewise, we've got 3 and 3 in these, so these need to have 1s. And this one has 6. So that's fine. And this one we'll come back to in a moment. Now, if we do the same thing in the opposite direction, we can see 1, 2, 3 ones. That's odd. We need an extra 1 to make it even vertically in the second dimension. Likewise, 1, 2, 3. So we need an extra 1. 1, 2, 3. We need an extra 1. 1, 2, 3, 4, 5. We need an extra 1. But this one has 4. That's already even. So we don't need an extra 1. So we put a 0 in down there. And then the last two have 3 each. 3 is an odd number. We need an extra 1. So now we've calculated 7 parity bits in the other direction. And we need to calculate the first dimension parity bit for that to complete the byte. There's 1, 2, 3, 4, 5, 6 ones. We don't need an extra 1 to make it an even number of ones, so we put a 0 in there. So now we have this two-dimensional parity check. And if you like, try changing different bits and seeing how each time you will cause the parity in one or the other direction to change. See if you can find 4 bits that you can change that won't change the parity result. It's a little challenge for you to do. And we'll do the internet checksum algorithm in the next video.